Hi, I'm Professor David Farina. In today's lecture, we're going to be talking all about the solar system, in particular, the formation of the solar system. Let's get started. The formation of the solar system. Today's modern theory includes nebular contraction. So what this means is that we start off with a mass of nebula. A nebula is simply a big cloud of matter that's floating around in outer space. And for one reason or another, maybe a supernova goes off nearby, or maybe we get a shock wave from the birth of another star that's nearby. But for one reason or another, we've got contraction of the nebula, and eventually gravity starts to take over and pulls matter closer and closer and closer together. Now, as we have this nebula moving around, it's got random motion, it's moving in all different directions. Eventually, a preferential direction is determined. Just from randomness, we get order. And as that turning starts to take place, rotation starts to occur. We've got a flattening of the disk that starts to happen. It's similar to if you were spinning very, very fast. It would be hard to keep your arms from flying outward. So the matter that's on the equatorial region of this, perpendicular to the rotational axis, you'll notice that it's wider, it's a disc shape, and then if it's in this orientation with the rotational axis, it's flattened down in this orientation. So this flattening and squishing of the disk also allows the disk to spin faster, which only flattens and continues the process. Maintaining angular momentum is very important here. Now, as the nebula starts to flatten out, we end up with some areas that are hotter, we have some areas that are cooler, and we start to get the formation of planetesimals through a process called the condensation sequence. Now, this is a really important concept, so pay attention. As we go farther from the sun, of course, is a very hot object, and its radiation is pouring out into the solar system after the sun starts its nuclear fusion process, which is basically gravity pushing down and condensing the material to the point where the atoms are actually going to physically bond together, a process called fusion. So once this process starts, we have the condensation sequence starting to take over, and the things that are in the very, very close proximity to the sun are going to have very, very high melting and freezing points. Things like rocky planetesimals. Whereas as we go farther and farther out towards the edge here, the temperatures drop off dramatically. And as they do, we eventually get things that are more lower melting and freezing point. And those icy and liquidy bodies that are out farther are going to be the icy planetesimals, which will eventually form into gas giants. We see, once again, this is happening around other stars as well, and we can monitor their progress, and we can get an understanding from a statistical standpoint on how solar system formation occurs. This particular star, Beta Pictoris, has a disk of warm matter, and it's in its earliest stages of planetary formation, possibly. Now, the conservation of angular momentum law says that the product of radius and rotation must be constant. So as the dust cloud collapses, its rate of rotation must increase. So when we talk about condensation of solids, we look at Mercury, Venus, Earth, and Mars. We find that the observed density of our inner planets are actually rather high when compared to the outer planets, which we'll get to later. Okay, and this is a very important table, so I'm going to just remove myself here for a second. Sorry about that. And you'll notice here this says the condensation sequence and then the temperatures at which each of these various different materials condense at. So at 1500 Kelvin, which for all intents and purposes, this is approximately 1300 Celsius, we've got metal oxides. So molten metal. As we go down here, we've got molten iron and nickel. We've got silicates. Notice temperatures still very high, things close to the sun. Feldspars, which are made of large amounts of rock on Earth. We've got then finally a very important substance here, water ice. So water ice is freezing and melting point is 175 Kelvin, which is about zero. It is 0 C Celsius and 32 Fahrenheit. So this is an important step. The condensation of water is key in the formation of Jovian-like planets like Jupiter. So as soon as we get to the point where water ice is able to condense out of the solar nebula, we end up with Jovian planets, which include these materials rather than the heavier and less common metal oxides and silicate materials. Hopefully that was clear. So temperature in the protostellar cloud is going to decrease outward. So we've got hot in the center, cooling as we go out, and terrestrial bodies, once again, silicates and metals, whereas we've got Jovian planets, which include those more gaseous-like materials. This important change of chemical composition, we end up with a lot more material to work with because there's a lot more gas than there is metal. So what basically happens here is that planets start clumping material together to create planetesimals. I liken this to if you didn't clean your house for a number of weeks. So eventually you'd start to get some dust bunnies on the ground, and those dust bunnies would grow bigger and bigger and bigger and bigger. If you didn't clean your house for 3 years, the dust bunnies might get to be so big that they now have the ability to attract things to them. So this is similar to what's happening with the planetesimals. They grow bigger and bigger and bigger over time, and as they get bigger, they have more ability to clear the nebula around them, similar to those dust bunnies collecting other things from the floor. Sorry I got this cut off here. Let me once again get this out of here so that you can see the text. So, as it says here, gravitational instabilities may have helped the growth of planetesimals into protoplanets. So when you've got areas where gravity is a little bit higher or a little bit lower, this creates little rotations in the solar nebula and therefore spins up planet growth. Get my face back here for you. Sorry about this. So the protoplanetary process of growing protoplanets, there's two running theories here that we could potentially have. On the left, we could have a model where we have the material is originally more rock and metal, rock and metal, rock and metal, and then heat from the actual process of formation cause what we call differentiation to occur, where we have a solid metal core and a liquid metal core, and then more silicate materials as we go farther and farther out. The second possibility is that the first planetesimals contain mostly metals, then later planetesimals contain mostly rock, then rock mantle forms around the iron core, then heat from the formation starts to partially melt the planet, and eventually you end up with a planet that looks identical. So one of these two growth possibilities comes up with the same outcome. So we've got the same looking planet here, but two different ways to get there. So the simplest form of this would, of course, be unchanged composition over time, that the matter accreted in a particular order. This outgassing process, where we have the material forming in this order, is thought to be one of the running theories for how Earth and other planets in our solar system were formed. So, some improvement on this scenario: gradual change of grain composition due to cooling off of the nebula and storing of heat from potential energy could have continued to drive this right-hand process a little bit faster and made it a little easier to make planets like we see today. So is there a Jovian problem? This is a kind of interesting topic. So I'm going to keep my face turned off for a second here so that we can see these two diagrams. The first diagram you can see is moving now. We've got the growth of these planetesimals into bigger and bigger planetary bodies. And we've got the semi-major axis on the x-axis here, showing us that their distance from the sun in astronomical units. And we can start to see some planets forming around 1, 2, and about half an astronomical unit. And some smaller planets forming elsewhere. Notice the time scale in the top right-hand corner. We're at about 140 million years, and the solar nebula is almost gone. We're going to start that over again, and we're going to start the other one down bottom as well. So the one at the bottom there includes a Jovian planet here. Direct gravitational collapse is something that we think might be possible. In other words, we've got the ability with a large planet. It has so much gravity that it actually can pull things into it rather than just through an accretionary process, which means it needs to actually touch in order to stick together. So the idea here, and you just saw it happen again, is Jupiter may have collected material as it moved its way through the solar system. And this particular Jupiter here is something called a hot Jupiter, which we'll talk about more in our extrasolar planets conversation. Let me turn my face back on here so I can see you all. So here's the basic story of planet building. So we've got protostellar material, and that protostellar material is less than 15 Earth masses. We get planet formation through accretion, Earth-like planets. If we have more than 15 Earth masses, we have planets that grow via direct gravitational collapse, Jovian or gas giant planets. So once again, the temperature of the cloud here, you can see a different diagram. We've got high temperature metals. Earth forms on that part of the curve, and the distance is our x-axis here. So if we're close to the sun, we've got high temperatures, which mean we only get metals and silicates. As we go down, we have water ices, melting point and freezing point, and Jupiter-like planets all of a sudden can start to be formed. And ammonia ice also plays a role in places like Saturn, and then other various types of ices in Uranus and Neptune, and the outermost planets, and Kuiper Belt dwarf planets like Pluto. Now, the age of our solar system is determined using a number of techniques. One of them is radiometric dating. So radiometric dating basically means that we're looking at the isotopes of a radioactive element, and we're watching it over time. And as the radioactive element decays, it has something called a half-life. Half of the material, 50% out of the 100% we started with, remains after one half-life. And we monitor the amount of one material, the red one was the parent material, versus its daughter isotope, parent and daughter, and we can determine, based on the ratio of these, how many half-lives it has gone through. So after 2 half-lives, we have a quarter of the amount remaining. 1/2 times 1/2 is 1/4. After 3 half-lives, we have 1/8 of the amount of the parent material remaining, and 7/8 daughter isotope. 1/2 times 1/2 times 1/2 is 1/8. So in dating the Earth, we have used, and also with the moon and meteorites, we've kind of taken a survey of all of these objects, and we've come up with a 4.6 billion year old solar system age. We can see once again the solar formation process around other stars, and that concludes our lecture today on the solar system and the formation of our solar system. Thanks for watching. Please like this video and subscribe if you have not done so. Thanks and have a great day.